Hello, everybody. Welcome back to day two. First speaker is Mark Gross, and he's going to tell us about partial compactifications of modular K3 surfaces inspired by mirror symmetry. Okay, cool.
Okay, thank you again. This is actually, what I'm talking about is quite an old story. It was work that I started sort of in discussions with Sean Keel and Paul Hacking in 2009, and later on Bernd Siebert got involved. And there's been a manuscript which has been circulating probably for at least 6 or 7 or 8 years. It's been a little bit hard to keep track. Time has been flying. However, I've been sort of returning this recently and trying to get that manuscript into a publicable or releasable form. And in particular, sort of bring up some of the techniques up to date with modern technology. So most I'm going to talk about what the motivation is and try to state the main results, what the vague ideas behind those main results are. So the story starts with sort of going back to 1993 with a paper of Dave Morrison. This was a paper called Compactifications of Moduli Spaces Inspired by Mirror Symmetry. Now, this was in the very early days of mirror symmetry, and it was speculation based on experience and looking at the sort of examples that physicists have been playing with over the last couple of years in the early 90s. And I actually think it's a remarkable paper in the kind of mathematics that end up inspiring. So let me say a little bit about what the basic situation is. So suppose we have X a Calabi-Yau manifold. And let's take MX to be the moduli space of complex structures or complex deformations of X. So I'll draw this as something like this, MX. And maybe we want to think about compactifying this in some way. All right, so of course, this is, for example, quasi-projective variety. In fact, of course, moduli space could be found as a quasi-projective variety, at least you could polarize X. Then, of course, you can compactify, so you get something, compactified thing. Now, the most important point for mirror symmetry are certain deepest strata of the boundary. Now, there's a rather long and technical definition of the sort of deepest strata we consider called large complex structure limit points. Let me. So intuitively, this is kind of the worst possible degeneration we might have. Typical example would be, say, degenerating a quintic threefold to union of hyperplanes. And I'm not going to give the technical definition, but this includes maximally unipotent monodromy. Okay, so associated to each such large complex structure limit point, so I'm going to write these as LCSL. Mirror symmetry suggests that associated to each large complex structure limit point let me say yi, we might have a whole bunch of large complex structure limit points, is a mirror Calabi-Yau. which I'll call yi, with Kähler cone KYI containing H2YI coefficients in R. Okay, so that's the cone generated by all, or the cone of all classes of Kähler metrics. So there should be something more. There should be a rational topological domain. Which is a subcone of KYI. And in general, the Kähler cone could be something awful. It could have some straight parts. There could be some limit points for edges. There could be some round bits. The Kähler cone can be sort of something that's truly awful, but we should be able to find inside here a rational topological cone. This is KYI, and this is PYI. And this rational topological cone should be a fundamental domain. I should probably set cone here with one domain, which is a fundamental domain. For the action of the automorphism group of yi. Okay, so this is already, so the statement that you can find such a rational topological cone is already sort of a deep conjecture. So existence such a rational topological cone is already a deep conjecture called these days the Kalmata-Morrison cone conjecture. So Kalmata and others have done quite a lot of work on it. It's known in certain situations, but it's, I would say, for a general Calabi-Yau threefold, it's certainly not known yet. Okay, so what do we have so far? So for the conjecture, again, this is when I say mirror symmetry suggests, the conjecture is that to every one of these larger complex structural limit points, one can find a mirror Calabi-Yau and this extra data rational topological cone. And further, MYI contained an M bar YI, oh, sorry, MX, MX contained an M bar X locally near YI. Looks like a compactification of the tube domain, or a partial compactification, I should say. Of the two domain H2YI are square root of -1, Kähler cone of YI, modulo, so first of all, integral shifts in cohomology. So that would be a usual tube domain defined by the Kähler cone YI, but we also divide out by the automorphism group of YI. And with this partial compactification determined, like the Satake-Bally-Borel compactification determined by the data PYI. Okay. So this is sort of general philosophy. The idea is that somehow the structure of the Kähler cone of the mirror tells you something about a good local compactification on the original moduli space, that this compactification data is controlled by data on the Kähler side of the mirror. Now, of course, when this was written, there was a huge amount that was unknown. For example, just constructing mirrors, there was no general construction for mirrors. Of course, the Kawamata-Morrison cone conjecture still isn't known. But there has been some progress. And the first point is that we now know, so with work of myself and Siebert in sort of papers from 19 and a slightly different approach from 2021, we have general constructions for mirrors associated to maximum unipotent degenerations. Okay, so one could then ask how much of this of Morrison's picture can now be pushed through. Obviously, without the Kawamata-Morrison cone conjecture, we're still a long way from being able to push that through. But what I'm going to talk about is the story in the K3 case where any sort of suitable cone conjectures are known. So let me start with now specialize in the K3 case. Maybe I should ask if there are any questions, but I imagine asking questions is a little bit difficult being remote.
Wait, can I ask a quick question? This is stupid. Maybe, I don't know. What's the difference between a maximum, oh, can you hear me?
I can barely hear you. I might be able to rectify that by turning my volume up, but
I think
I suspect you're probably too far away from the microphone.
Did I miss something? Oh, geez, this is really bad. Can you hear me though?
Yeah, now you're coming through very clearly.
Okay. You were talking about Morrison's being a large complex structure limit point, but now you're talking about maximally unipotent degenerations. What's the contrast you're making here? Or
So maximally unipotent is a weaker condition than Morrison's large complex structure limit.
okay.
So there was a lot of extra information, extra requirements.
Okay. I didn't know. Okay, great.
Okay, so the story in the K3 case. So let's take so fix a lattice. So there's some standard theory of moduli of K3 surfaces. So if we fix a lattice M in the integral cohomology, so I'll always write this H2. And I'll just write that as H2 of K3 is the rank 22 lattice given by the second cohomology group of K3 surface. And let me take a very specific one with M being generated by a single primitive element. H2 of K3 and H squared equals 2n. So this is a polarization. Think of this as polarized, giving a polarization for K3 surfaces of degree 2n. And then we split M perp. So I'm taking the perp with respect to the intersection pairing on H2 of K3 as M perp is equal to U orthogonal direct sum with M shack for some lattice M shack, and where U is usually called the hyperbolic plane. This is the rank 2 lattice generated by two elements E and F with E squared, F squared equals 0, and E dot F equals 1. Okay, so if I do this, note that because this lattice has index 1 and or signature, well, signature 1. This has signature 1 minus 1. This has signature 319. That means that M perp has signature 118, and hence can correspond to so in particular is rank 19. It can be the Picard lattice of a K3 surface. Sorry, and this is incorrect. I want to write M check, not M perp here. Okay, so we have a moduli space of M polarized K3 surfaces. So I will write this either as M sub the lattice M, or as it's more frequently written, Fg, G is equal to N minus 1. This is the moduli space of K3 surfaces with a polarization whose hyperplane section genus is N minus 1. So this is the moduli space. Put another way, this is the moduli space of polarized K3 surfaces with primitive ample divisor of 2F. Okay. Now, again, there are sort of various ways, known ways of trying to compactify this moduli space, these Bailey-Burrell-Satake compactifications. And let me give you how this, so what kind of data you need to do that in a simple case. So let's C be a connected component of a cone, so X in M check R, tensor the lattice M check with R, and I want X squared to be positive. Because the signature of this cone a priori, this set has two connected components, so we choose one of the two connected components. Then provided N is square free, this is a technical assumption, and it reduces the amount of data we're going to need to specify everything. In fact, a suitable choice of fan right, it's delta prime on C determines the toroidal compactification. Fg contained in F bar G. I'll write the superscript delta prime to indicate that it depends on delta prime. So when I say fan, of course, I do mean a fan consisting of strictly convex rational polyhedral cones, but generally it's quite an infinite fan. This cone is very curvy. It's as given by a quadratic equation, and the fan has to be infinite. I don't really know how to draw such a thing, but it's going to fill out this cone with an infinite number of rational polyhedral cones. And there's various group actions, which again, I don't want to go into detail on because it starts to get rather messy. And the various each cone has to be a fundamental domain for this group action, or it has to be independent of a fundamental domain for the group action. Okay, but anyway, there is this standard way of going from such data to produce what's called a toroidal compactification of Fg. Now, philosophically, the general problem with these toroidal compactifications is that there isn't any natural modular interpretation. We don't necessarily have the family of K3 surfaces degenerating over the boundary of this compactification. And so in a sense, our main interest was to actually build a family over this compactified moduli space. So here's the main theorem, and then I'll talk about sort of my part of my contribution to this main theorem. Is so given the following, the data above, so given delta prime yielding a compactification, there exists a refinement delta of delta prime, giving some kind of toric blowup of this compactification. Toroidal blowup, because these aren't actually toric varieties. So such that, okay, a number of good things happen. So first of all, there exists a canonical extension of the universal family. Of course, these as stacks, because universal family only exists as a stack, of the universal family over FG to a family of polarized Gorenstein K-trivial, so trivial canonical class, semi-log canonical surfaces. Pi from X, there's some polarization X01 to F bar delta G. Now, there is still a bit of an issue. I don't want to make any false claims in this talk, and I just want to add there's still details to work out. Over what's called the type 2 locus of the boundary. I.e. boundary points where the monodromy isn't maximally unipotent, but still a bit bad. So there's quite a lot written in this manuscript about this case, but I haven't yet had a chance to go through it and really vouch for it. And I think there were quite a few details that still need to be filled in. So view this as a statement of work in progress and what we hope to do. But it's certainly solid over the type 3 locus. And this is one reason why I put the word partial compactifications in parentheses in the title of the talk. Okay, so the second point is that the degenerate surfaces over the type 3 boundary. Again, type 3 boundary are those boundary points with maximally unipotent monodrome around them. Are unions of projective toric, unions of projective toric varieties. Okay, so the third thing, and the thing that I think we were most excited about, is that there exist so-called canonical theta functions. So what does this mean? So i.e., formal neighborhood of the type 3 boundary there exists a canonical basis for the d twist of OX of 1, of OX rather, well-defined up to scaling each basis vector individually. Okay, so there's the main theorem. Sorry, it doesn't all fit on one page there. Now, the theta functions, this is something that those of you who've seen my many talks on mirror symmetry will probably have seen these theta functions in a fair amount of generality. These are generalizations of theta functions for abelian varieties. Theta functions for abelian varieties have been known since the 19th century, can be viewed as canonical bases for ample line bundles, sections of ample line bundles on abelian varieties. And if you apply this whole procedure that I'm going to tell you about today to the case of abelian varieties rather than K3 surfaces, you actually get those classical theta functions. So these can be viewed as a generalization. Unfortunately, one of the big mysteries remains as to whether there are some intrinsic properties that these theta functions satisfy, which would explain why they're so special. But they come out of our construction. Okay, I pause for questions.
Can I ask a question quick?
Mm-hmm.
Do you know the product structure of these theta functions is enumerative in any way?
Yeah, so the whole construction comes out of our general mirror symmetry construction. Indeed, the product structure is enumerative.
Thanks.
Okay. So in the remaining time, let me tell you something about what the basic construction is for doing this. So the point is, we've known since the early 90s, thanks to work that I mentioned of Dolgachev and Nikuin and Voisin, we know what the mirror to this family of genus G K3 surfaces is. So mirror, so this is usually called the DNV. So DNV is Dolgachev. Kulin Voisin mirror. Family. So remember, we had this rank 19 lattice M check. And so this is M sub M check. So this is moduli space of M check polarized. K3 surfaces, i.e. we have a primitive inclusion, i.e. K3 surfaces with a primitive inclusion, M check contained in H2 of K3 lattice, and with some positivity conditions, which I won't go into. So it's not hard to see. So this is the mirror family, and there's been a lot of study of mirror symmetry in this context of K3 surfaces, partly because it's really all very explicit in terms of lattice theory and moduli of K3s. So in general, M check is non-compact. but it is one-dimensional. So it does have a rather simple compactification. And again, the best situation is when n is square free, and that's why we restrict to this case. There is only, well, maybe I should say we can compactify. M check contained in the compactification because it's one-dimensional, it's unique. And in fact, furthermore, up to some natural form of equivalence, there's only one maximally unipotent boundary point. Provided n is square free. Again, this makes life rather a bit easier for us. Okay, so we have this moduli space, which is some Riemann surface, or a compactified moduli space, and we have, again, up to this notion of equivalence, we have a maximum unipotent boundary point. Now we can take a small disk around this maximum unipotent boundary point. I'll call this disk D. And we can restrict the universal family over this moduli space to D. And then we can compactify it. So we obtain over D a choice of compactification. Say normal crossings, compactification. Y over D. Okay, so we should have, say, 0 in D of Y0, and Y0 is the normal crossings variety. Okay, and then the general fibers is a M check polarized K3 surface. Okay, so the point is we have this unique maximally unipotent monodromy point. We can then build some choice of family of degenerating family of M check polarized K3 surfaces over this disk D. Now, an important point here, very important point, is that there's not a unique extension of the family over the puncture disk to the central fiber. There can be many choices of models. They're all related by birational transformations. So important note. Many possible choices of model Y, and they're all related by, but they're all birational to each other. Okay, so we often call this is the DNV family. Call this the or A maybe, because it's not unique, A DNV degeneration. Okay, so now, in some sense, the first punchline is that we can apply the general setup that Bernd Siebert and I carried out. This is precisely a situation where we're able to construct mirror. So we now apply a GS construction of mirrors. So this involves a certain amount of work. So one has to first choose some data. So this requires some choice of data. So first of all, we have a strictly convex. Actually, I think this is now there's only one choice of data here. A strictly convex rational polyhedral cone sigma contained in the relative divisor group contained in the relatively ample cone. And this gives a dual monoid. Shall write as P. That's the intersection of the dual of this cone sigma with the relative group of curves, and this time integers. And this necessarily contains all effective curve classes. Okay, so if you haven't seen this notation before, let me just say a few words about this. So this is the group of divisors, so group of real divisors modulo numerical equivalence. And when I talk about numerical equivalence, I'm testing and I'm intersecting with compact curves, and therefore those curves have to be line fibers. So tested on curves. Sorry, this is a bit smaller than I was hoping. Curves on fibers from Y to D. And then this is the group generated by curves contained in fibers of Y to D, modulo numerical equivalence, again tested on divisors. Okay, so fairly standard Morey theory. Okay, so what do we do with this? So given this data, my work with Siebert constructs a mirror family. Shall write as X hat over spec of K bracket P hat. Maybe I should stick to the complex numbers here. And now I should tell you what this thing here is. So where C bracket P is the monoid ring of P. And the hat means completion, C bracket P hat. is the completion with respect to the monomial ideal. Generated by elements of P minus 0. Okay, so that's the maximal ideal, the maximal monomial ideal of this ring. Okay, so this is something you can just apply without any effort. We get a mirror family, and these things will be families of sort of in some sense generic fiber, will be an M polarized K3 surface. So let me just say here that the method, this would be a talk of itself, but I think many of you have heard me talk about that before. Method is the mirror is constructed, the homogeneous coordinate ring of the mirror. Is constructed using a type of Grove-Witten theory called punctured Grove-Witten theory. Which is something developed by Abramovich, Chen, myself, and Siebert. So, when Robert asked about whether there was a number of interpretation, in fact, the product structure on this ring is given by some punctured Grove-Witten invariants. Now, unfortunately, this isn't kind of the end of the story. Otherwise, it'd be very short. Well, fortunately, unfortunately, it'd be a very short paper if this was the end of the story at this point. But there are a number of basic issues. So the first one is that this only gives a mirror family over a tiny space. So what do I mean by this? Well, if you think about the compactification that we're looking for a compactification FG containing FG bar. So let me draw the boundary. Remember, the space is 19-dimensional. What we're doing is we're producing families in formal neighborhoods of certain zero-dimensional strata. Right, spec. Right, this is a spec of this. This is a very small piece of this whole story. The second issue is that it's actually the wrong dimension. In fact, it's not really even giving a family over some neighborhood of a boundary point of FG bar. It's giving a family that's too high dimensional. So our family is the wrong dimension. As the dimension of this vector space of real divisors is actually 19 plus G. So the 19 comes from the Picard group of the general fiber of this DNV family. The general fiber was N check polarized, N check was rank 19, so you expect to see a 19 showing up. But the G, this G comes from irresistible components of the central fiber. So both of these are problems and means that we can't use sort of just out of the box. We can't use this mere construction. We're simply getting families that are too big, and we're getting families who are too big a dimension, but are too small a piece of the actual moduli space. Too big and too small. Okay, so how to fix these problems? Okay, so mostly I will talk about one because somehow two is rather technical. So here's the important aspect. This, as I mentioned earlier, this model Y was not unique, and this is a fundamental fact about birational geometry in 3 dimensions. We have many possible compactifications. So there are many different birational semi-stable models of our family Y to D. And any two of them are related by a sequence of flops. So this is something that's in the K3 case has been well understood since Kulikov's work. And in a sense, that was some of the origins of the whole program of minimal model theory in higher dimensions. On the other hand, under flops, so N1 are vector space, sorry, I was using A here, our vector space A1, Y over D, coefficients in R. This is independent of the model. If two models differ only in codimension 2, then they have isomorphic Picard groups. And if you let the model vary, the ample cones, the relatively ample cones, fill up a possibly infinite, produce a possibly infinite fan in this vector space. So the ample cones, all relatively minimal, models Y prime to D, Y to D, fill up the cone in A1 of YD, and the resulting fan we call the Mori fan of Y to D. Okay, so we have now a similar picture to what we had before. We have a bunch of ample cones for the various models, and they fit together into some fan. Now, of course, these ample cones tend to be very far from being finite rational polyhedral cones. But fortunately, in this case, we do know a lot about the Kawamata-Morrison cone conjecture, and you can show that there are nice fundamental domains which are rational polyhedral for the action. So this can actually be subdivided. The Mori fan can be subdivided into a rational polyhedral fan. With good behavior with respect to all the various group actions. Okay, so that sort of is a complicated story, but that's actually one place where we're using what is known. There's work of Kawamata in this case that allows us to get a good refinement of this Morey fan, which a priori is a union of not well-behaved cones. Okay, so associated this, so let's call this Morey fan sigma. Sorry, just turned to the wrong page of my notes. There we are. I'm doing sigma delta. Okay, so what tends to happen, so as you go between chambers of the Morey fan, well, of course, maybe you subdivide and nothing happens as you go between two chambers. But in general, if you pass from one chamber to another, this will correspond to a flop. Say y to y prime to y double prime. Now, you can also then look at the toric variety corresponding to delta. Now, of course, delta is not a finite fan. This is some horrible infinite type toric variety. But the various zero-dimensional strata in this toric variety correspond, of course, to maximal cones in the Morey fan, and hence correspond precisely to the situation we had in the general construction of mirrors with Siebert. So what we have is, so far, we have in sort of these formal neighborhoods of these zero-dimensional strata, we get Gross-Siebert construction. Of mirrors. And then the key point is, if you go into a much deeper analysis of that construction, you can then extend the mirror construction along the entire toric boundary that's visible here, the entire toric boundary corresponding to these interior cones separating faces. So you can now extend the construction along toric strata, or along formal neighborhoods of toric strata, of formal neighbors of toric strata corresponding to smaller dimensional cones in the Morey fan. Okay, so that is the sort of heart of the analysis. For those few of you in the audience who have seen the original manuscript, there was some sort of truly awful ad hoc way of doing this. That part's getting rewritten right now using the more modern construction, and we hope it's going to be a bit more readable. But that's kind of the main idea that's I'm currently focused on. So this is the type 3 boundary. Okay, so I'm almost out of time, so let me just sort of say a few words about what happens next. So as I say, this fan is living in a 19 plus G dimensional vector space. All right, so these families are simply too large dimension, but there's a nice trick, which I'm not going to go into the details of. There's a nice trick for cutting this down. So for 2, there exists a trick for cutting down the dimension of this family. To 19. So it's not particularly hard, but it would require sort of setting up quite a lot of notations. I'm not going to do that. Once you've done that, what do you have now? You have this 19-dimensional family over some formal neighborhood in a toric variety. That family has some nice structure. You have various group actions, wild group actions, etc. Automorphism groups of K3 surfaces acting on this toric variety, acting on this formal completion. Everything behaves well with respect to those group actions, but we still have to relate this to FG. So the final step is to glue in the produced family into FG to obtain a compactification. Again, this will essentially be F bar G delta equipped with a family. Of degenerating K3 surfaces. Okay, and so for this we use period calculations, which are pioneered by Rudot and Siebert. Okay, so it's a rather long story, but hopefully this gives some ideas to what to expect when this paper finally comes out, which I hope it will this year. Anyway, it's progressing. Yeah, so thank you for your attention.
Are there any questions?
I have a question. Can you hear me? Mark, can you hear me?
Yeah, I can hear it. Yeah.
Yeah, I wasn't sure about this microphone. So for a type 2 degeneration, we have pieces on the end which are like I don't know, like P2 with a smooth elliptic curve. And then how does the GS construction for like the whole thing interact with the GS construction of the like Del Pezzo pieces on the ends of the type 2 degeneration?
Yeah, so this is something I'm sort of rather reluctant to go into. And the reason I'm reluctant is that it's a part of the paper I haven't succeeded in reading. So there is, as I say, there's some sort of rough draft. And that part was mostly written by Sean with help from Paul, with lots of things like this. These details need to be filled in. So I think my understanding is that the basic construction, so somehow, if I go back to this picture, let me draw a little bit more. You might have, so what I've drawn here might be sort of type 3 locus, but then over here, we meet a bit of type 2 locus. Now, of course, in a type 2 locus, you won't see the moduli of elliptic curves showing up. What we do get from the Gross-Siebert construction will just be a tiny formal piece of that going off in this direction. And so we can't extend our construction to actually get a family over the entire type 2 locus. So my understanding is that Sean is basically constructing that piece of compactification by hand. And then the tricky part is to show that it actually glues in with the bit constructed by myself and Siebert. So maybe in a year's time, when I give this talk, I'll be able to explain that, assuming it holds up. But I'm very reluctant to say this is a theorem at this point.
Great, thank you. And I guess if you think about the future, is it like going to the next dimension? Is that just totally hopeless, or maybe?
So the major issue, I mean, that's something that would be very nice to do. And the issue is that, what are we really doing here? Is that when we go between cells, between cones, we're doing flops, which we understand. Analysis of flops for degenerations in K3 surfaces, that's, as I say, that's been known since work of Kulikov in the 80s, I think. And what we do is we just understand how our construction is affected by each of the types of flops that can occur in that case. Now, if you go to, let's say you go to one more dimension, so your total space of the degeneration is 4-dimensional, you have very little understanding of what the flops can look like, and then somehow we have to analyze how things like the logarithmic Grove-Witten theory, how the puncture Grove-Witten theory changes under these flops we don't understand. Not to mention that we'll no longer necessarily have smooth models. So it's a little bit, or maybe I should say it's more than a little bit imposing as to what might actually happen there. So I think some fundamentally new ideas would be needed to push to higher dimensions. Of course, the other point is that without the Kamat-Morrison cone conjecture, you don't get very far.